Hello, I'm Brian Davis, and I'm presenting work done in collaboration with my advisor, Brian Morse at Brigham Young University, Brian Price, Chris Tensmeyer, and Curtis Wigington at Adobe Research. We'll begin by looking at OCR and document understanding. OCR is the task of reading the text in an image and often retrieving its location. Document understanding is interested in higher level information. What is the meaning of the words? What information do they convey? In this work, we focus on forms, so it's form understanding. Like pictured, forms are defined by fields with labels and values, and some hierarchical elements. Recently, form understanding has been addressed as two distinct tasks. Entity detection, or entity labeling, which is finding out which texts form a single thing, an entity, and what that entity is. Is it a header? Is it a question? Is it an answer? Entity linking, or relationship detection, is finding out the relationships between the text entities. This is the answer to this question. This question is under this header. In this work, we've primarily focused on the entity linking, although we do also solve entity detection. The current state of the art for document understanding is dominated by the transformer. Transformer models are very effective, but they are also very data hungry in their pre-training requirements. Now, the pre-training does need to only be done once, but I feel like these transformers are missing something, and that is computer vision. I don't think they have strong enough visual components. But have no fear. We introduce here a visual form understanding model, which uses no language, requires no pre-training with extra data, and performs entity linking almost as well as the transformer models. This is visual FUDGE, form understanding via dynamic graph editing. FUDGE injects visual features which include context information for potential relationships into a graph convolutional network. FUDGE predicts several edits to the graph, which eventually lead to the final prediction. Entity linking is a very visual task, which humans can do without reading the text, relying just on layout and visual cues. Because FUDGE is language agnostic, it can be applied to domains where OCR is difficult, and should generalize even to other languages. Wait, you say, some of those transformer models you talked about are doing vision. They have CNNs in them. That's true, but let's go ahead and take a look at some of these prior works a little more carefully. The most common inclusion of visual features involves passing the image through a CNN, but then forming the visual features by region of interest pooling only around the word bounding boxes. This is what Layout LM version 1 does, and is done by Vibert, Grid, and Tilt, which are both being presented at this ICDAR. Only taking visual features around words clearly leaves out much of the contextual information of the document, such as separating lines that may occur between words. Now, Vibert, Grid, and Tilt both use a UNet CNN, so the region is going to potentially have a wider receptive field, but I still feel like it's not the best way to analyze the visual space. Brose was the state of the art at form understanding at the time we were writing the paper. Brose doesn't use any visual components, just the text and spatial information, improving on the original Layout LM. Layout LM version 2 improves the original Layout LM with better use of spatial information, with the introduction of spatially biased attention, and by including much stronger visual components. They run the image through a convolutional neural network with adaptive pooling that breaks the image into pieces, forming visual tokens that together describe the entire image. These tokens can be attended to along with the word tokens. This is able to capture contextual information the word bounding box extraction method is not. However, it must learn to attend to what visual tokens might be important for a given task. Layout LM version 2 includes 1D attention along the tokens in addition to the spatial attention. Because the token order will often follow the read order, but is not meaningful in the visual domain, the 1D attention will likely favor text, leading to an imbalance in the strength of modalities. FUDGE builds directly on our previous work on visual form understanding we presented at ICDAR 2 years ago, and follows the same general pipeline of detecting text lines, forming a graph, and making predictions using region of interest pooled features. In FUDGE, however, we replaced two key components, the heuristic graph creation and the classifiers and the post-processing. I'll briefly go over the high-level description of FUDGE, and then we'll go into each component in more detail. We first detect text lines using a convolutional neural network, which differs from most other methods which use the dataset provided OCR word bounding boxes. We do lines. Using the text lines as initial nodes, we propose edges between these nodes to form an initial graph. Rather than directly predicting from there as we did previously, the graph is processed by a graph convolutional network. This graph convolutional network predicts edits to the graph, which modify it. It is then passed to further graph convolutional networks for additional edits. After 3 passes, the graph is at its final prediction. Using a graph convolutional network eliminates the need for the post-processing we did before, as the graph network can predict over the entire document coherently. Our detection CNN is a VGT type network, but includes dilated horizontal convolutions to be able to predict long text lines. This is the exact same network we used in our previous paper. The graph is created by predicting where edges should be between the nodes. The nodes are initially the detected text lines. We take each possible pair of these and give them a score by coming up with some spatial features between them regarding their relative location, their size, their class, and pass this to a small 2-layer multi-layer perceptron. We then threshold this for high recall to give us our initial edges, which will be pruned later. Our graph has features both on the nodes and on the edges. The node features use the features from the CNN and take the text line bounding boxes and region emitters pool features from them. This is similar to what other models have done. The edge features are more important, as they include features for the entire region of a potential relationship. It uses the bounding box that surrounds both of the text lines, and again does region emitters pooling. We use the general graph convolutional network framework described in Battaglia et al. This alternates between updating node and edge features, and we use residual connections in ours. The node features for our network are updated by aggregating the incoming edges using dot product detention. Everything else is just appending feature vectors and running them through a 2-layer multi-layer perceptron. The graph convolutional network predicts a new class at each node. And for each edge, the graph convolutional network predicts the edits. Whether that is to prune an edge, simply to remove it from the graph, whether to merge nodes to correct an oversegmentation, or merge them to group text lines into a single entity. When merges are performed, the graph features are averaged for those nodes, and the visual features are actually recomputed for the new bounding box and reintroduced. At each edit step, we are refining the graph, although most of the changes happen in the first edit. Because of this, the first 2 graph convolutional networks have more layers than the last. After the 3 edits, the final graph is predicted. Because the output features from one graph convolutional network are fed to the next, together they could be viewed as a single long graph convolutional network where the graph simply edits at certain points of the network. We evaluate on 2 datasets. The FUDGE dataset, Form Understanding and Noisy Scan documents, which are modern printed documents which are scanned at a fairly low resolution. The other dataset is the National Archive Forms dataset, NAF, which is forms taken from the United States National Archive. These are a higher resolution but are much noisier in general than the FUDGE dataset. To better compare to prior methods, we create a slight variant of FUDGE we'll refer to as Word-FUDGE. Other methods have generally used the dataset provided OCR information, which we like to allow FUDGE to see to improve its bounding box detection. However, other methods use the word level annotations, whereas FUDGE has been operating at the text line level. To train Word-FUDGE, we simply use the FUDGE model, but substitute the text line predictions for the dataset word bounding boxes. Because FUDGE can correct oversegmentation, Word-FUDGE simply learns to merge the words into text lines. We compare against 4 prior methods. Carbonell et al. Is not a transformer model. Rather, they place the word embeddings along with spatial features into a graph and use a graph convolutional network. They use no visual features. Layout LM, a BERT-based model, incorporates some spatial features and weak visual features. BROS is another BERT-based model, building off of Layout LM. It uses no visual features, but instead incorporates better use of the spatial information. And Layout LM version 2, as we talked about before, incorporates the spatial features in a better way than the original version, and also includes better visual features. Unfortunately, neither vibrant grid nor tilt evaluated on FUDGE. In comparison to these other models, FUDGE is a model which uses no language information but does incorporate visual features. We'll look at entity linking first. We are so far the only ones to use the NAF dataset, which we introduced in our previous paper, which, as a little shout out, we would very much appreciate if people used it. We outperform our prior work, which isn't terribly interesting. On the FUDGE dataset, we can see that while BROS has a significant improvement in performance over prior methods, Word-FUDGE approaches its performance. BROS was a model pre-trained on millions of documents, whereas FUDGE was trained on only the FUDGE dataset. Layout LM version 2 did not evaluate entity linking. However, Layout XLM does, although they only evaluate the question and answer relationships. As we can see, FUDGE is still competitive and actually beats Layout XLM if it only fine-tunes on the FUDGE dataset. The transformer models perform much better than FUDGE on entity detection. Language appears to be a stronger modality for this particular task. However, we do outperform Carbonell et al., which is another graph convolutional network approach, which uses the language modality instead of vision like our own. So why is FUDGE, a model without any pre-training, performing so well compared to models pre-trained on millions of images? First, FUDGE is only a contender on the entity linking task. It's far outstripped on the entity detection task, even by vanilla Layout LM. The FUDGE dataset is relatively small, especially if used from a natural language perspective. A large transformer can easily overfit to this and requires the extensive pre-training to avoid this. FUDGE, however, with a little bit of data augmentation, never overfits to FUDGE, at least as far as we've trained it. Additionally, entity linking is a fairly different task from most of the pre-training tasks the transformers use, meaning they're not benefiting as much from their pre-training on this. Our FUDGE was specifically built with entity linking in mind, and thus has specific architectural biases that benefited over transformers. Transformers are much more general architectures, which do allow them to be applied to other problems. Here are some qualitative results I flashed up earlier. Anywhere there's a red box, there's a missed detection. Anywhere there's a red or yellow linking line, there is a missed or false positive relationship prediction. While FUDGE is performing entity linking at a level close to models like BROS and Layout LM version 2, it can be seen that neither these nor FUDGE are solving the problem adequately. So what is needed next? FUDGE has been an investigation into how far we can go without language, and we're happy with the results, but we don't think this is the final solution. Strong language information is obviously a valuable asset, and we hope to see future works in this area marry the concepts of strong language modeling with stronger computer vision. Thank you for listening to our presentation on FUDGE, Form Understanding via Dynamic Graph Editing. Please come check out our code.